In the previous segment, we talked about motion in 1D, that is generally known as rectilinear motion, and in this segment onwards, mostly it will be on curvilinear motion. In fact, the previous segment, which was about rectilinear motion, was just in a way recap of what you have already studied in your 12th standard, but these topics on the curvilinear coordinates will be somewhat new to many of you. Okay. Now, when we say curvilinear motion, what we mean is say a particle is moving some random path in 2D. Yeah, so to make it clear, so this segment will be for 2D, and then we will go into 3 dimension in the later segments. Okay. Now, having said that, in 2D a particle will move in some random path like that, as opposed to moving on a single line like that, okay, which was the rectilinear motion. Now, then how is it then different from this? So, the main difference comes from the representation of the position vector and its derivatives basically. Now, here just one variable was sufficient because it was 1D problem. So, one variable was sufficient to define the displacement, and which we denoted as S, and then we just plotted everything. So, the visualization also was with respect to displacement versus time, velocity versus time, etc. Those 5 kinds of different representations we discussed. But as opposed to that, in this 2D, how we will represent is generally we will define some coordinate system. For example, this is x and y coordinate, for example. They need not be the only coordinate system. We will see in fact many more types of coordinate system. And then we will define a position vector r to the point. So, this is the point P which is moving, and we define the position vector r, which will definitely be say a function of time. Okay. And if we know this r as a function of time, then basically, so let me write like this. If we know this, so that means we know how the particle is moving with respect to time from some arbitrarily chosen origin of an arbitrarily chosen coordinate system. Okay. And then we define velocity as a function of time to be the change, means for example here, say at instant t the particle is here, and at instant say t plus del t the particle is say here, or t dash maybe. So, it was t and it is say r at t dash. Okay. So that is how it will move, and then this portion will be, from here to here is your delta r, right. Now, that delta r will define the change in the position vector, and that will define the average velocity. So, if we want to write say the average velocity, now V average, if we want to evaluate, so that will be delta r over delta t. So, that is where delta t is nothing but t dash minus t. Okay. So, and your instantaneous velocity v, so this will be the average, that is the total change by the total time, and the instantaneous one will be the limit of this when delta t tends to 0 of delta r over delta t. Okay, that means this position vector comes closer and closer and closer, and somehow it stays something at like that. Okay, and this being so now this one is the delta r in the limit that delta t tends to 0, and so this line now will become almost this will become tangent to the curve on which it's moving. Okay, so that is how we will define the velocity, and in the same manner we will just define acceleration to be just dv over dt, which will be nothing but d square r over dt square. So that's how we will. So these three things primarily are so RT, VT, and AT. So these are our focus points. Okay, so and in full kinematics portion, these are our concern. Okay. Now, having said that, so coming to how to visualize, if you remember, we visualized through graphs when we were talking about the rectilinear motion like this. But here, this is one of the representation which can be used to visualize the motion, where we are basically showing the position vector with respect to time, how it is changing. Then, so this will be called, a path. This is the path, and at any location, the tangent will give us the velocity. Okay, so if I draw here, so a tangent here, or if I draw a tangent here maybe, so these things will give me the velocity vector, because that represents the dr over dt. So that will be the direction, and depending on the magnitude of that vector, it will be the velocity. Then there is another way to represent or visualize this motion is by this. Take any arbitrary point, say C or whatever, and then plot these velocities starting from this. For example, say v at initial time is, say, this, so v is 0, then say v1 or then v2, so like that we keep on drawing the velocity vectors starting from here, and then the curve joining that. So basically we are talking like that. Now this curve will be called a hodograph. Okay, like if you plot the position vector and join the tips of them, all the position vector from some origin O, and then join the tips, you will get the path, and from there you get the velocities and draw them and join the tips of the velocity vector, you will get the hodograph. So that means here the tangents, if you take, so they will represent the accelerations basically. Okay, at a different time. So because these are again functions of time, everything is a function of time. So these also will represent the motion in curvilinear, when the motion is curvilinear. So these are two ways in which they can be represented, which give different kinds of information. Okay, so from here directly you can see the acceleration directions, and there you can see the velocity directions, and yeah. So now, but these, the visual representation, they are for getting a feel about how things are happening. They don't give us any quantitative information on what exactly is happening and how the velocity and acceleration are changing. And if you remember, we are majorly concerned with the acceleration because that is what the kinetic will mean, acceleration times mass is equal to force, which actually is acting on that particle at that particular time. So that is our concern, to find out the acceleration. So these curves, though they give a qualitative information, quantitatively they are not very effective. Now, to have a quantitative analysis of all these things, we generally will have to write these equations in some mathematical functions or using some mathematical functions using some coordinate system. So, based on some coordinate system, and that we will see in this segment and the next for curvilinear in 2D. For example, the first one is our Cartesian coordinate system. Okay. So, this all of you are quite familiar with, okay, in which we have say a bad drawing. So, an x axis, a y axis, and then that is it, and then any point. So, any position vector now will have, say, a position vector r as a function of time, say, can be represented as, say, like this. Its x coordinate. So, if I draw like this, so it's the x coordinate, which is also will be a function of time, and its y coordinate also will be a function of time. And so that is what we write. This is a function times I, say the I is the unit vector in x direction, j is the unit vector in the y direction. So this can be written as y as a function of time times j. So that is how we will represent any position vector as a function of time, and then it's very easy to see that to calculate the velocity, the instantaneous velocity, we just differentiate, that is dr over dt, and now onwards we will mostly represent this term as r dot, because when we put a dot, it will mean invariably a differentiation with respect to time. So it's a short notation for this, and that will give us. Once I'll write explicitly like this, but then next time onwards I'll just put a dot on that. Okay, so this I plus d y of t by dt and j, or in short form we write this as x t dot I plus y t dot j. So these, so just note that these are differentiation of a scalar function. So x is a scalar function, and y also is a scalar function of time, and then it's just their differentiation with respect to time, and this is differentiation of the vector r with respect to time, which is a scalar. Okay, and then acceleration we can simply write as r double dot. It means I am differentiating again this with respect to time, which will be nothing but x double dot t I plus y double dot t j. So that's about the Cartesian coordinate and how we calculate the velocity and acceleration given the position vector. For example, say you had say a projectile motion, right? When you throw a ball in a uniform gravitational field, then your x velocity remains constant. So you can say that your x of t is nothing but the say u naught is the initial velocity in some angle with an angle of theta you have projected. So u naught cos theta is the horizontal component which doesn't change times time. Okay, so that is how the distance will change, and similarly y of t will become u naught sine theta t minus half g times t square. Okay, so that's how your these x and t, so this and this function will change like that, and you will just have the rt r of t is nothing but this xt I plus y t j. Okay, so that's how you generally would write, and then you will get velocity and acceleration vectors by just differentiating these functions with respect to time. Okay, fine. Anything else that I wanted to talk about this? No. Fine. Then, and then it's very simple. I mean, and then there is nothing to talk about much because these are very, very obvious. The way we have done the differentiation and everything is very obvious. Fine. Then, is it so that we can represent only in terms of x and y? Okay, that means the Cartesian coordinate. Is it the only coordinate system through which we can represent r? The answer is definitely no, and there are reasons which we will discuss now. That some other coordinate system also are generally used to represent and analyze motion which are curvilinear. So the next one which we will discuss is the polar coordinate system. Okay, polar coordinate system. Now what is done in this is, suppose a particle is moving on a certain arbitrary curved path, then we define very arbitrarily some direction to be our x axis and y axis. Okay, though finally they won't directly come into our equations, but we have to define some direction and some origin so that we will measure some angle and some distances. Now what we will do, we will use we will join the origin to the position of the particle at a particular instant, and in this direction we will define ER to be the unit vector. Okay, so and then this distance will be the not r vector. So this distance is r, and this is its unit vector. So we will define a unit vector in this direction. That means at every point on the path or during the motion of the particle, the direction of this unit vector is changing. Okay. So, please note that that is a very important difference from what we had in the Cartesian coordinate system. In this, suppose the particle was again moving in some arbitrary path. Now, but wherever the path was or wherever the particle was at a different instant, the ij were never changing, they were static, they were fixed. But now the way we are defining a unit vector, that is changing at every location. For example, now if I go to this point, now the position, so the unit vector becomes this. Suppose this is at time t1 and this is at time t2. So, like that we define the unit vector which is continuously changing. And then the other because in 2D we will require two information to exactly pinpoint where the thing is. So, this gives the distance information, and from this x axis whatever we have defined, we measure the angle theta of that radial vector, and that theta gives us another parameter to completely specify this, and we define the other unit vector, and we call this E theta in this direction. Okay, in the same direction in which the positive direction of that is in the direction in which we measure this angle theta. Okay, so that is how we will measure E theta or define E theta in fact. Okay, so these are two unit vectors. So, for example, when we come here, ER is defined like that, and we draw a perpendicular to that, and E theta is defined like that. E theta is defined like that. So, everywhere this is 90 degree. Okay, so these are all orthogonal coordinate systems. In fact, orthonormal coordinate systems, because ER and E theta are of unit length. Okay. Now, this is one of the very important way to represent curvilinear motion. Okay. And that means what we have done here, we have represent our r vector. So, now the position vector will be given by what, r, which is this length basically, times ER. So, this is the unit vector representation of the position vector. So, if you compare with this was like a component representation, right. So, in Cartesian coordinate system we represent mainly like a the component representation, but in polar coordinate once we come there, so or polar coordinate system, and sometimes it is called r theta also. Okay, r theta coordinate system. So, there we represent the position vector primarily in terms of unit vector representation. Now, if that is so, then how to calculate the velocity? Obviously, this will be r dot. Okay. So, that means we will have to differentiate it. So, now, but there are two terms now in the unit vector representation which are multiplied. Okay. Now, let's how to differentiate it? We will have to do r dot times ER. So, that is the product rule of differentiation I am using, plus r times ER dot, right. So, that is how we should do. See, earlier also in this, when we differentiated this, we in fact should have, or we had actually differentiated this also, because this is also a product form xt and I, but this I was not a function of time then, because it was always fixed with respect to time. So, that is why in fact here we did x dot times I plus x times I dot, which was 0. I dot was 0 because I was not changing with respect to time. But now exactly the opposite is happening. Here ER is not fixed anymore. ER is changing with respect to time. Okay. So, this point generally creates the initial confusion among students, and they always feel that maybe this way of representing our unit vectors which are changing themselves may be more complicated, and why it should be of any use. But we will see that it will make life much easier, and for handling complex situations this is a very useful representation. Okay. But then a vector has to be represented in terms of only unit vectors, not in terms of unit vector and its derivative, right? A vector has to be represented only in terms of unit vector. So, that means this is not exactly the form which we require. So, somehow we have to manage this, we have to figure this out, what this is. Now, let us see how to think about it. Think that suppose at time t, ER was here, and say at time just a little bit after that, your vector has come here and your ER is here, ER at t plus dt, or t1 I will write because I was writing t1 there, that is fine. But while writing equation I will just write t. Okay. Now, just what we will do, we will bring these vectors, we will join them tail to tail, and then you know that we can do without affecting their existence, because the vector is a vector wherever you put it. Okay. So, that means I will just draw here say ER at t and ER at t plus dt. Okay. So, that means this now is the d of ER, right. But then the lengths of these vectors are what? One unit length. So, that is what I said, they are orthonormal basis. So, that means these lengths are unit vectors. Okay. If these lengths are unit vector, what can we tell about its length? Will it not be just this angle d theta, whatever this angle is? Now, if this angle is theta, then so that means DER is nothing but in magnitude. I'll write here that your say d, or yeah, that's fine. I should have written maybe delta, doesn't matter. I'm thinking in terms of the limit when delta t tends to 0, so that you know the process of taking that to be delta t and taking into the limit, but I am just writing it like that, so you understand what I mean by this. Okay. So, dr magnitude is nothing but d theta. Okay. And what is its direction? Because you see, as soon as this becomes almost coming and coinciding with this angle will become 90 degree, isn't it? So, that means this is pointing in the direction of E theta. So, that means this has a direction of E theta. Okay. That means now we can calculate, say ER dot to be in the limit. So, here I am just writing for clarity, d of ER over dt when del t tends to 0. So, that means here I will just say that so this one is nothing but your delta ER magnitude is say delta theta by delta t, okay, in the limit 0 times E theta. And so that's what we can write as this one, theta dot or d theta over dt times E theta. Okay. So this is a very important result which you should always keep in mind with complete understanding. ER dot, sorry, ER dot. Okay. So differentiation of ER with respect to time is nothing but theta dot, the rate at which the angle is changing of that vector, times and then it is in the direction of E theta. So that means now we can do one thing. I'll just move these things a bit up so that I'll get some space. Okay. So this always happens. Sorry for that. Okay. Yeah, now I think it's fine. Yeah. Still this moved, but it's fine. I'll just put it again. So ER dot was here. So this now I can write as, say, this is R dot ER plus R theta dot. So this I am replacing with theta dot E theta. So this is nothing but V. So that is our expression for velocity. Okay. So this is very important to observe. Okay. Now can we then write the expression for acceleration which we always wanted to, right? So let's go to another page and so let's start with the expression for, let me write from the beginning. So R is nothing but R E R, then V we calculated to be what? R dot E R, say R dot E R plus R theta dot E theta. And then let's calculate A. A will be, first we will have to differentiate this. So again it's a product and we are differentiating a product of two functions. So R double dot ER plus R dot ER dot. So this is the first term getting differentiated, plus we will have to differentiate this. So let's first say differentiate this part, which is again a product. So R dot theta dot plus R theta double dot. So this is the first term getting differentiated, plus E theta plus R theta dot and E theta dot. So these are the differentiation from the second term. Okay. Now there are two problems. One is this and the other one is this. Okay. So that means they are not in the form of unit vectors, other things are in the unit vector form. Now how to think about E theta? Let's go to the previous page. See here. Now E theta at t was in this, and maybe at t dash, which is t plus t dt, was maybe in this direction. So if I draw again tail to tail, those two vectors, I'll do what? I'll get something like this, isn't it? So E theta was, say, E theta at t was like this. Was it in that direction? Oh no, yeah, that's fine. And sorry, and then your E theta prime, which is, this is E theta at t plus delta t, and that means the difference here is this. So this is delta E theta. Now you see that this is in the direction of ER. If you compare here, that diagram you see here. So that difference is actually in the direction of negative ER. So that means again this length will be nothing but 1 times this again d theta. Okay. So that means I can just write here like, you know, E theta dot will be nothing but magnitude wise it will be d theta over dt, because this is the length, so d theta by dt, and its direction is in the negative r, right? So that means I can simply write negative theta dot er. So, and this we already have derived, so I can write here the expression of A to be equal to say r double dot er plus r dot, and er dot is theta dot, just see here, er dot is theta dot E theta. So here I will write r dot, okay, theta dot E theta plus, these are fine, r dot theta dot E theta plus r theta double dot E theta, plus r theta dot, now this is E theta dot is this, so minus theta dot ER, fine. So which will be equal to, now I will just club the similar terms. Now ER is here and here, right? So let me write them together. So R double dot minus R theta dot square times ER plus, so these are in the direction of ER and other all terms are in theta, E theta direction. So there are two terms like that, so 2 R theta, R dot theta dot plus R theta double dot, and this is E theta. Okay. So that becomes your acceleration. Okay, fine. Is that all which I wanted to talk about this? Let me check, or do I have something else? Okay, that's it. So we have what? These are expressions for radius vector or position vector, velocity vector and acceleration vector. So you have to just understand and should be able to derive them at any time. Okay. Good. So these, okay, just before we stop this segment on the polar coordinate, I just want to make a point here that where is it, or what is the motivation behind using such set of values, for example the distance and angle. You remember, or do you realize that it's, you know, suppose there is a ground somewhere like that, and you have suppose a radar, and which is, you know, tracing a aircraft which is moving like that. So that means here you always measure the distance from here, from the reflection of the wave. You can measure this distance r like this, and from the angle the radar is making, you can always get this theta. So these are the kind of applications where you measure the distance and the angle at which the object is moving. So in such type of curvilinear motion, see here this need not move in a straight line even or in a circle. This could be moving any path whatsoever it likes to move, but always this r versus theta will be available. And so that is one point about the application where the polar coordinates should be very naturally coming into picture. And one more point I want to make is, generally students have a notion that polar coordinate means that the particle should move in a circle. It is not at all a requirement. A particle could be moving in any arbitrary motion, and it is just another coordinate system like your x, y or the Cartesian coordinate system, through which you are just representing everything, and then by that you are just getting the acceleration. And because you are measuring these things, you remember the radar problem, you are measuring r, so continuously over time, so you can always measure r double dot from that, you can calculate that. Similarly, you are measuring theta as a function of time, so you can evaluate this. So all these terms you see, they can immediately be calculated from the measured values, and then you know er et theta, so you can simply calculate acceleration, and then convert these er e theta to the xy coordinate, and you have in ij unit vector at any instant of time if you want it to be in the Cartesian coordinate system. So that is the whole story about the Cartesian and the polar coordinate system. And in the next segment we will be talking about another coordinate system which is very similar to this but slightly different, which is the normal and tangential coordinate system, and for short we will call it NT coordinate system. So see you in the next segment.